So today I'm going to present on a paper that I published at Supercomputing Workshop Canopy. And so this is a little more kind of tweaked for this audience. But if you're interested in all the fine details, there is a paper out there. And I'm happy to help point you to it. So this is a variation of that presentation. As we go through, feel free to ask questions. I'm happy to discuss any of this. So today in this presentation, I'll be discussing a separated model for running rootless, unprivileged PMIx-enabled HPC containers in Kubernetes, which is an incredible mouthful. So let me give you some perspective on really what all that means. So we wanted to explore how to move towards more of a microservice model for MPI jobs in Kubernetes, something that kind of breaks it into something Kubernetes is more familiar with without really hurting the usability of an MPI kind of a model here. And what we found, there's a number of challenges in doing so, mostly around performance and functionality preservation, but also you'll see security becoming a bit of an issue. So, but there's also really good opportunities for doing this work, right, and moving into the Kubernetes model. You have a lot more, some dynamic flexibility with new MPI models such as MPI sessions. You can take advantage of some of the features of the Kubernetes environment. So there is some motivation to doing all this work. In a traditional HPC model, we're launching with the MPI job with a launcher like MPI run. So as you can kind of see here at the top. This is going to start a daemon on each node, as we know, or it might reuse established daemons. And often the daemons are launched via a mechanism, often like SSH, as you see here, though not always. It's typical. These daemons will then fork exec each MPI process, and the MPI processes communicate to the daemon via PMIx, and the MPI processes communicate with each other on node via shared memory and off node via high performance interconnect. In a vision for the microservice model in Kubernetes, what we want to do is we want to move the runtime daemons and have them exist as part of the Kubernetes infrastructure. And so possibly a daemon set is the idea here. So this would be part of the Kubernetes environment, the infrastructure itself, that's set up for you. And then we would put the MPI application in kind of a separate context. And so the MPI, so if the daemon set's part of Kubernetes, the application itself is part of the job that you launched, right? And so you can launch multiple jobs against the same daemons in kind of a persistent model. And so in Kubernetes, we would often use a stateful set for this. They're numbered and a little more structured in order to do that. And the other benefit of separating these two would be to allow the runtime infrastructure to be persistent on a system and integrated with Kubernetes, and free the MPI application from being built for a specific resource manager, right? Because now we're pulling the resource manager away from the application. And as you'll see, we're going to use PMIx to really bridge that gap. But before we can make kind of this leap here, there's a couple steps that we have to go through in order to really explore all of the aspects of this. So in this presentation, we're going to explore the steps towards this goal. And so the first step is to take a look at how we map HPC into Kubernetes today. What is the typical model here? So the traditional mapping of HPC into Kubernetes puts the runtime infrastructure in the same container as the MPI process. So it's not part of Kubernetes, it's just another aspect of the container, such as the GROMACS container will have an MPI runtime in it. So this is kind of a one big container image and a pod with many processes in it, the daemon and the application processes. And the pod is kind of the virtual work unit inside of Kubernetes. It defines namespaces for it to run in. And so this is the most direct mapping from a traditional HPC model to running in Kubernetes. And there's papers out there that kind of explore this. I'll talk a little bit about each one of these Kubernetes objects in a moment. So if you're not familiar with those, hang on, I gotcha. In this presentation, what we wanted to do is step towards a microservice model by splitting the application and the resource manager, which is something that we'll eventually need to do here. So what happens when we start to separate these two? What problems arise? And then in the future, so what we're not going to cover is this last step, right? How do we take what we've done here and take it that last mile and actually integrate it with Kubernetes into a more persistent manner, right? And I'll talk to you about a little bit about that as well. So in the traditional model of mapping MPI into Kubernetes, we need to set up a number of Kubernetes objects. And I'll discuss these in a moment. These are kind of on the right here. But additionally, we have to set up a container, right? This is the thing that we're going to run inside of Kubernetes. And this application container, let's say GrowMax, if you're running GrowMax, it must contain a launcher, such as MPI run. It must contain the cross-node launching service, such as SSH. And finally, it must contain the application itself with all the libraries, the data, and the binary. Now, there's a number of problems with this model. It's likely that the runtime and cross-node launching service needs to be customized in some ways for the Kubernetes environment. And each Kubernetes environment may be a little bit different. So this could easily lead to something that happens all too often with these HPC containers is you end up having N versions of it, each for a specific environment, even though the application core itself isn't too different. It's really kind of the runtime, the pieces, and that can get out of control if it starts to happen. It's a really slippery slope. But most critical for kind of our motivation is the inclusion of the cross-node launching service in the application container. Most often this is SSH, particularly if you look at a lot of these HPC containers for Kubernetes, they'll just throw SSH in there because it's easy and it's widely supported. The problem is that SSH exposes an attack vector into the system, but the responsibility of securing SSH over the long term is now the responsibility of the application container maker, right? The GrowMax container maker, whatever. And it's a non-trivial burden, right? If there's a compromise there, if there's a setting you miss, suddenly you have to be an expert in that as well as assembling this container, and that's a burden. So this attack vector via SSH is a growing concern in the Kubernetes community to the point that it's highly discouraged in their documentation and even in some environments completely prohibited. You cannot put containers on there that have SSH in them or that run the daemon. And so the community is trying to figure out how to get around this. And even some of the MPI job mechanisms like in Kubeflow, they have alternative mechanisms, and I'll show you some of those in a moment. So in this effort, in the separated model presented here and then the associated Canopy paper, we're exploring separating the runtime and the cross-node launching components from the application into two separate container images. So what does that buy us? Well, the Kubernetes objects are going to stay the same. We're not going to mess with those in this work. We're just pulling apart the previous HPC container. The first container is the runtime container, or the REC, as we'll call it. The REC includes the runtime environment, so MPI run. Put Slurm in there, so be Slurm, JSM, whatever PMIx-enabled runtime you want. And then the cross-node launching service will also exist in the REC. The intent here is that the system administrator defines and maintains this container, not the end user, right? So the REC container can be maintained by those with the most knowledge of how to secure these components over time and can roll out new versions continuously on the system. They might have a variety of them too to support multiple users, but really the ownership of that is with the sysadmins who are also securing the broader system. The second container is the application container, the app. And this includes the application itself, right? It's smaller, focused, and more portable as a result. And it contains just the libraries, the data, the binary for the application itself. And as we'll see, the PMIx will be our connection between these two. And so the most critical point here is that the app creator is no longer responsible for maintaining and configuring the REC portion of the environment, which is the most prone to security vulnerabilities over the scope of the app itself, the app lifecycle itself, and could put the host system at risk. That's our big benefit here. So let me take you through what we had to do and some of the pitfalls that we found along the way. So first, let's review the Kubernetes objects that create what I typically like to call a virtual cluster for HPC applications in a Kubernetes environment. So in this diagram, you can see how different Kubernetes objects relate to one another, such as the service, the job, the stateful set. So let's walk through these a little bit. So the Kubernetes namespace itself, this provides a context in which to group all the Kubernetes objects within our virtual cluster here. The RBAC, or the role-based access control, is composed of a few objects seen here that define how Kubernetes objects can interact with one another and the broader system. So this tends to be a security-focused specification. There's a headless service. Now this is a service that's configured in a special way to be what they call headless. It provides DNS services within the virtual cluster for any components that need it, right? If they need to translate compute node 0 into an IP address in the overlay network, this headless service will do the translation for them. It's a private DNS. The stateful set is going to create a replicated set of pods on each each of which is going to represent a node in the virtual cluster. So these would be your compute nodes, and it's running the container image from the user. And lastly, there's going to be a job object, and this will represent our login or launch node from which the application can be launched. Now, the job isn't strictly necessary since you could always SSH into or log into the first node in the stateful set. But as we'll see on the next slide, it's a really helpful point of entry, and it provides some interesting, useful services as a result. So it's handy to have. So the job object, which you see the specification for here on the right, is useful in a couple different ways beyond just being a login node point of entry. There exists a race condition between when the job pod starts and when all of the stateful set pods start, right? Since the job is one thing, if we let it start up at the same time our stateful set, which is say 1,000 compute nodes, when that job starts up, it's going to start running the script inside of it. And so maybe it calls MPI run right at the start. Well, if all of those compute pods aren't there, MPI run's going to fail to launch on nodes that haven't spun all the way up yet. And so it'll fail right away. And so some of the existing infrastructure that's out there, what they'll do is they'll say, oh, you just put it in a loop. So it's going to keep failing. And you just, while it's failing, keep launching it. And eventually the stateful set will come up and eventually it'll launch. And that's messy and terrible. The better way to do it is to hold the job pod so that it doesn't run the script until everything's started up, right? Until all of those nodes are up and running and ready to go. Kubernetes itself doesn't have a batch scheduler or a mechanism to do this for you. There is a Kubernetes working group. There's a batch working group, which is investigating kind of the scope of all of this now. There are a couple third-party projects that add kind of batch and game scheduler capabilities to the system with kind of limited ability to kind of do this, but there's really nothing built in. So what we did here, without relying on something else, we wanted to build something. So in lieu of a batch scheduler, we created what's called an init containers that does two things for us. And so this is kind of this part here. The container piece down here is where we'll actually run the MPI job. So here's your job script. Here's the init containers. So what this does is it'll run this container before this one's allowed to start. And so this will allow the init container to say, okay, I'm going to look out into the cluster and make sure all of the stateful set pods are up, all of the services are up, everything is stable, and then I'm going to let the job run. And that'll solve the initialization race here. The other thing the init containers does is generate a host file for us, right? Because we can scale the stateful set from 1 pod to 1,000 pods, we'll need a host file in order to know, here's the full set of resources we have, just like you would in a batch system. So what this init containers will do is it'll first wait for the cluster to come up and be stable, and then it'll write a host file down to a shared mount. And so this init containers is going to write the host file into op HPC ASC, which is a shared volume here. So once the init containers is done, then the login node will be able to see that value. And here we're setting it up as a default host file. So Pertay will pick it up right away. But if you have a different resource manager, you can do different things there. And so init containers, pretty handy. It's just an aspect of a job. So this is another reason why we might want to keep the job around. All right, so we have a stable cluster, we have a host file. What we want to do is figure out how to separate the rec from the application. The rec's still going to have to fork exec the application. The rec is executing in one container, and then it's going to be creating additional containers within inside itself. It's nesting containers. And this is not a common thing to do, as we'll see. But it is possible, and it's possible in a few different ways. So let's take a look at that. So now that we have the virtual cluster, what happens when we separate the two containers? Well, Kubernetes is responsible for starting the runtime container in each pod of the stateful set. We're going to say, okay, Kubernetes, here's the rec, stamp them out for me. Now the runtime container is then going to be responsible for starting the application container within the same pod. Kubernetes does not have, currently anyway, sufficient ability to start a new container inside an existing pod after the pod's been created. It does have a newish concept of what they call ephemeral containers, which are meant for debugging. So you have a Kubernetes job running, you want to spin up a debugger inside of a running job so you can kind of attach to it and inspect. That's the purpose of these new ephemeral containers. The problem is when they brought it through to the standard, they really needed to limit the scope of it, and they tightened the scope around it too much and to the point where it cannot be used for our needs here. It's too tightly scoped to support MPI shared memory, for example. And so we looked into that and it kind of came up short. Now, eventually they might fix that, which would be great. But for right now, it doesn't. That leaves us with two main approaches for nesting containers. The first involves exposing the bare metal host container runtime socket all the way into the rack for it to start a container. So this would be your Docker, your Podman, or your Containerd socket that Kubernetes is using, just pulling that all the way through into your rack. Now, this is scary because it exposes an attack vector between the bare metal host and the application along that socket. And for that reason, it's really shied away from. Now, the second approach, which now that we have rootless container runtimes that are much more mature than they were a few years ago, is to install a rootless container runtime inside the rack, something like Podman. And so Podman will actually start up a container without needing something from the system. Now, the subtle issue there is that it does need, even though it's a rootless container runtime, it does need some form of privileged access to mount a file system, right? So the mount privilege. And it needs to mount a very kind of slim file system just to spin up the container image itself, just to kind of lay out the container image and start the exec into it. Let's explore that, right? We don't want to expose the host socket. Let's explore if we can solve this issue with this mount piece. So there are two techniques for handling the privileged access for Kubernetes for rootless containers. The first is to make the pod fully privileged. So this is very similar to if you run containers just bare metal, you can add the privilege option and then it has root on your system, right? Very similar here, similarly scary here, right? So as soon as you make a pod fully privileged here with the security context, it exposes an attack vector. And in most Kubernetes configurations, this is completely disallowed. If you try to submit something that asks for privileged, it'll reject your request. So that's really a bit of a non-starter for us. The second is to expose the fuse file system, so user space file system, into the pod using what's called a device plugin object inside of Kubernetes. Now this is the same technique, a similar technique to how NVIDIA Mellanox exposed InfiniBand and GPU devices into the Kubernetes pods today. So this is a commonly used production technique here. And so what we're going to do is we're going to use this fuse device plugin, which you see a link here to the implementation, and it's going to expose dev-fuse file system into the pod, but nothing else. So we don't need privilege on the system. All we need is this access to this user space mount point. So instead of asking for everything, we ask for the very specific minimal need we need, right? So we're really focusing the exposure here. All right, so we figured out how to nest containers. Let's turn our attention now to the cross-node or maybe termed cross-pod launching piece. So the rec needs to start a runtime daemon in each pod and establish the runtime for the application before it can start the application containers, before it executes the app. This currently happens in one of two ways inside the Kubernetes community. In the SSH daemon model on the left, the pods often run as root and idle in the SSH daemon waiting for connections, right? So it's just waiting there. You don't have to run the SSH daemon as root, but I'd say the vast majority of containers I've seen out there do so because it's easy to configure. There's lots of documentation on how to just turn it on and go. And that's what a lot of containers are looking for. The problem is they turn it on and go, but they don't secure it. And this becomes the problem. From an application developer community perspective, I don't really blame them, right? They have a lot of other things on their mind than securing this, which is part of the goal here. So the launcher is going to SSH into each pod using the host file generated by the init container. Alternatively, you can use this kube control model, where in the kube control model, you install the kube control command line application itself, and then you use it to drop into the various pods instead of SSH. And so in the kube control model, the pods are going to wait in a pause loop. And so you'll see this pause process. It's very similar to the Linux init process, and it's going to be running as the user itself, as the embedded user. So instead of running as root, we can run as this MPI user I created in here. And so this pause container is just going to idle out there, and then we're going to use a wrapper around kube control exec in order to SSH into the pod. And this is the wrapper. This is all of it. and it can work across namespaces. So it's not super complicated, and it's well built into the kube control. Both options work fine. SSH model has the disadvantage of being actively discouraged by the Kubernetes community because of security responsibilities required by the container maker. Additionally, it's common to run as root in the SSH daemon mode, which is problematic, particularly if you mount a file system that is not user namespace aware. So this gets a little funny. The kube control exec model can be slower, however, to launch the daemon since it needs to bounce off the Kubernetes API server in order to resolve and route the exec request. So it's bouncing off the API server instead of the DNS as the SSH would. And so we found that it's slower, particularly as it scales. So in comparison to the SSH model, it will either SSH model will directly connect to the IP address it provided in the host file or bounce off DNS to resolve it. So a little bit of difference there, but two techniques, they both work fine. They can be equally transparent to the user. All right, now to the meat of it for us. So now that we figured out nested containers, cross-pod launching, let's turn our attention to how to pull these two containers apart and still allow them to interact with one another. So the two components need to interact with one another to perform operations like interprocess wire-up, dynamic process management. The PMIx library is going to serve this purpose over a socket connected from the runtime container, the REC, playing the role of the PMIx server, to the application container playing the role of the PMIx clients. The PMIx implementation installed in the REC must either be the same or cross-version compatible with the PMIx implementation in the application container, right? Because they're going to talk together, but the actual implementations of those libraries exist in two separate containers. So the socket, they need to be able to talk. So for this paper, we use OpenPMIx due to their cross-version compatibility support, which is another means of highlighting that this is an important problem for containers. Additionally, we're using OpenMPI. We're using the main branch, though the v50x branch would also work. We're using that as our library implementation since we can build it without the runtime environment. And this allows us to do two things: reduce the size of the application container, right? Because now we don't need PRT installed in there, for example. And for the purpose of this paper, better demonstrate that the separated model works in practice. And so if you're interested in how to do this, this is how you build OpenMPI without runtime. So let's launch. Now that the runtime and application containers can talk over PMIx, how do we launch everything? What does this look like from the user? So in this paper, we use PRT as the runtime environment. We created a little wrapper script that hides the podman complexities from the user and PRT so that you can execute PRT run or MPI run like what you see here from inside the container job pod or launch node, and just add this MPI image. You define the MPI image, which is your application container, and then you preface the command with this wrap container script. So let me open it up real quick, and you can see why we don't want to force the user to do this. There's a number of things here that we have to tell Podman to do in order to, one, get the rec talking to the app across the PMIx connection. But a lot of this happens, a lot of these options here are really just to get shared memory between the application containers to work correctly and efficiently. So let me take you briefly through the top. So it's important before we get started that when we say host here, we mean the runtime container pod, not the Kubernetes bare metal host, right? So the application can only access as far as the rack container, no further. And so that helps contain the scope of security a little bit. So the first one is the host network namespace. This allows the PMIx socket to be shared between the runtime and the rack and the application process and the application container that's nested. Next, we use the host version of UTS, IPC, and PID namespaces. What this really allows is the establishment of shared memory between the application container instances within the same pod using traditional techniques that are widely available and implemented today. So without having to change OpenMPI at all, this just works. Next, we note that the runtime daemon will often set a number of environment variables before fork execing the application container, things like here's where the PMIx socket is, for example. So we'll need to make sure that we pick up the environment from the host. Since we're nesting containers, we don't need additional C groups, so we're turning that off. Notably next, we have a cap add, so we're adding the sys ptrace capability. And this is completely for MPI's use of cross-memory attached single copy shared memory functionality, so fast shared memory. If you don't put it in there, most implementations will test and fall back to a slower shared memory protocol, and the double copy kind of technique that you can do. But if you want performance, which is one thing that we're also focused on here, you'll want to make sure to add this. And then lastly, it's often necessary to define a shared mount volume residing in the rec pod that the application pods can use to define a shared memory segment if they need a file system to rendezvous that with, right? Again, we're not changing OpenMPI at all. We're just trying to get them to use the same thing out of the box. So as you can see, most of the options allow the individual application container instances to communicate efficiently with each other and less with the rec itself. All right, let me give you a bit of a demo and then we'll wrap up here. All of the stuff you'll see here is archived in this GitHub repo. All of the scripts are there. Everything that we're running runs out of there. So feel free to take a look and experiment, fork it if that's helpful to you. So now that we've discussed everything, let's do the demo here. So I have a Kubernetes system of 18 Power 8 machines with InfiniBand and some NVIDIA GPUs in them. I'm using this version of Kubernetes installed via kubeadmin. I have device plugins, so Mellanox RDMA, this exposes the InfiniBand into the container so we can use the high-speed interconnect. We have the NVIDIA device plugin, which exposes the GPUs into the container so we can use GPUs. And that Fuse plugin that we mentioned a moment ago, which will expose the Fuse mount up into the rack so that it can start the application container, right? And that's the key. On the host, we're running RHEL 8.4 with Docker at the time of this. Obviously, if you're familiar with Kubernetes, they're moving away from Docker as a backend. They're not supporting Docker shim anymore, so we're moving the cluster over there. But at this time, it was still using Docker. In the rack container, it's RHEL 8.6 with Podman 4, and we were using Perte master at that time. In the containers, so in each one of the application containers, we have 3 application containers and then a rec, which is called runtime with Podman. They're all using OpenPMIx master, and for the purpose of this demo, we used the same PMIx build in all of them. We weren't here to test the cross-version support. We wanted to kind of keep it simple. So the containers form a bit of a hierarchy. Basically up here, we have our base RHEL. We install PMIx in it, and then we fork. So the rec is over here. We install the runtime. We install Podman. On the other side, we have the MPI containers, which do not have runtimes in them, and they do not have SSH in them, right? They're just MPI. There's one with NAS parallel benchmarks and one with GROMACS. So now we spin up the cluster, right? The virtual cluster here. So there's a makefile in this repo that hides some of the complexity. Feel free to crack it open. It's not too complex, but it does hide this to make it easy to start up the cluster. So you say deploy SSH with Podman unprivileged, which is our most secure variant in here. You wait for everything to spin up. By default, it'll spin up a cluster of 5 compute nodes. You can adjust that in the makefile to however you need. You'll see some of the Kubernetes objects here, right? You have your pods, you have your service, which is our DNS, our stateful set, which is our compute nodes, and then our job, which is our login node. There's a make command that says login, and this will run the kubeexec command to drop you into the rack. And at this point, it's as if you just SSH'd into the launch node of a cluster, right? It's a private cluster, only you were in there. To limit the scope a little bit, I usually get this question at this point. I'm not going to discuss user identity management in Kubernetes. It is possible to handle mapping your ID in and getting all of that to work with the file systems, but it's far too into the weeds for what we're trying to talk about to get into that. So for the demo, I just have an MPI user inside the container, and that's all we need. And then when you're done, you do an undeploy and it'll clean up. But let's look around the rack here real quick. So once we're inside the rack, once we've logged into this compute node, we see that we are this MPI user. And then we can cat the host file. Remember, this is written by the init containers. These are the IP addresses in that virtual overlay that's private to your cluster. From there, we do a Perte run and say, here we're mapping by 2 processes per node. We specify the MPI image for the K80's MPI. Here's that Podman wrapper script. So here in green, this is all executing in the rack on the login node. What Perte is then going to do is go out and it's going to launch this wrapper script, which will then start up Podman. It'll start up the container, and then it'll run this command in there. And it's going to be 1 application container per rank, per MPI process that's being launched. And this is just a simple little init finalize. It goes through and says, hey, there's 10 processes running, 5 nodes, 2 processes per node, which is what we map by up here. It's going to do an init barrier finalize and just kind of time it out there a little bit. So pretty simple little MPI, almost hello world. Next up, we do the same thing with NAS. So here it's the same PRT run command. We specify a different image, one that has NAS in it. And we're going to run the EP benchmark, right? Something simple. In the repo, I have all of them built, so you can run really whatever you want. If you want to play with performance, you can do that. But you'll see here that the NAS benchmark thinks there's 10 processes. It's going to use MPI to perform the calculation and return. Same thing with GrowMax. GrowMax itself, we're running the GMX MPI with MD run. We have a little benchmark in here that's provided by GrowMax that it'll run through and do 10 steps of. But again, you can see there's 10 MPI processes. It's going to use InfiniBand. It's going to use the GPUs if it can, because they're all in there, right? So the performance is very close to bare metal. All right, so I gave you a demo. Let me wrap up here. So in the Kubernetes HPC traditional model, containers must include the runtime and cross-node launching service in addition to the application. This not only increases the maintenance burden on the container maker, but it also introduces security vulnerabilities into the Kubernetes environment. This presentation of the separated model, we really focus on trying to pull apart the runtime environment and the cross-node launching service from the application container, and it yields some distinct advantages. First is the separation of concerns, which is an important one. The sysadmins maintain the runtime container, the REC, in accordance with the broader data center ecosystem and security requirements, right? If there's additional file system mounts or restrictions that are defined by the data center, those can be encoded into the runtime container itself. While the user can maintain the application container independent of all those complexities and maintaining them. So it makes the application container even more portable than it once was. Next is improved security. We removed SSH from the application container and put it in the hands of the sysadmin as part of the runtime container. Further, we can eliminate SSH from the runtime container by using the kubectl exec alternative or some other alternative specific to the broader system. Since that cross-launching mechanism is defined in the REC, the sysadmins now have the opportunity to define what that mechanism is. So if they have another alternative that they've developed that's more secure, more tied into their ecosystem, they can define that application container, doesn't have to worry about it at all, right? It's completely transparent to them. And lastly, there's an opportunity for improved performance due to the smaller application container size, since we removed the runtime cross-node launching components, and really set ourselves up to use persistent daemons inside of Kubernetes. And this will reduce the overhead of launching an application, as we see with any other PMIx runtime that uses persistent daemons. So a few notes on future work, right? Because we're almost to that microservice model, but kind of last step is what we need to do. First would involve consolidating this effort into a Kubernetes operator, involving a daemon set and kind of taking it that last mile and connecting it to the Kubernetes environment and making it a piece of it. This would advance the MPI-focused operators that are currently available, things like Kubeflow's MPI job, Volcano's MPI job mechanism, and it would advance those by using the separated model and being applicable to more than just MPI applications. Some of them are very specific to specific runtimes and MPI needs. This would generalize it a little bit. Now that the cross-node launching service is isolated in the runtime container, it's easier to explore alternatives to SSH and kubectl exec for cross-node launching. I've listed some rough ideas here. There are plenty of more that have been suggested, but I like the idea of isolating that into the runtime piece to give you an opportunity to really experiment without having to rebuild the application piece every time or adjust that in any way. Lastly, worth mentioning is that the development of a technique for application job scripts to become independent of the launcher being used would be really handy. So if you noticed as we're going through some of the demos, the job script itself, the thing that has to call MPI run or PRT run, must know the launcher in the REC in order to do that launch command, right? Once you get to the application piece, it's independent, but the job script that's setting everything up for the application really does need to know what the launcher is. It's possible to develop an independent tool that uses PMIx spawn to start the application against whatever runtime is installed on the system, be it Kubernetes, be it PRT, be it JSM, or whatever happens to be out there, right? And so the PMIx spawn mechanism could provide you that functionality. Need work, but it's possible. And so this would be useful not only in Kubernetes, but also traditional HPC systems. And so I've most recently heard this being kicked around in the MPI Forum's ABI working group. That is something that they might want to explore as something a little more general for application launching. So some food for thought here. But with that, I will conclude and ask for any questions.